This is our Physics 211, project number 1, by Eryn, Alexander Johnston, and Brooks Montoya. Now, the given equation that we are initially given to solve this problem with is the acceleration one. Now, this is the acceleration in respect to time, and that is equal to negative beta times little t divided by big T, x hat, plus alpha, parenthesis, 2 divided by 3 little t cubed over big T cubed minus little t to the fifth over big T to the fifth, and that's the acceleration in the y direction.
The objectives for the project are 1. Describe the motion of the helicopter. To achieve this objective, we made motion diagrams and graphs of the acceleration, velocity, and position functions of the helicopter, which were provided in the project video. These graphs and motion diagrams will be shown shortly. The second objective was to find how long the helicopter is in the air. In the project video, this objective was answered with the change in time equaling 2t, which is simplified down to 2 times the square root of 3d over 2 beta. The third and final objective for this project was to determine where the helicopter lands. This was answered by the equation written below of delta r of t, which has the x component being multiplied by d plus alpha of d divided by 35 beta in the y hat direction.
These are the graphs for the horizontal and vertical acceleration of the helicopter. These graphs were made by looking at the x and y hat of the acceleration function and graphing just the variable of the function, ignoring the constants. For example, the equation for the horizontal acceleration is a of t equals negative beta times lowercase t. These are the graphs for the horizontal and vertical velocity and are the antiderivatives of the acceleration graphs. These graphs were drawn ignoring the arbitrary constant that results from integrating because the original equation is symbolic and the arbitrary constant could vary for each graph. So we just drew a simple graph that is similar to what an actual graph would look like if all the constant variables were given a value. These are the graphs for the horizontal and vertical position and were drawn using the same process that we use for the velocity graphs, but instead of integrating the acceleration function, we integrated the velocity functions. The vertical axis for both of these graphs represents the position value, so the further the point is away from the horizontal axis, the further away the helicopter is away from the starting position horizontally or vertically.
Now, as you can see here, this is the motion diagram, and you can pretty clearly see that the motion diagram is nearly identical to the vertical position versus time graph. This mainly just being because the helicopter mainly changes in terms of vertical position rather than horizontal, as the horizontal one just increases over time. Whereas as you can see here, the vertical one, it goes up, it goes down, until eventually hit 0 again. And the reason it's not exactly like the vertical position versus time graph is that we set where the helicopter starts at the origin, whereas for the position equation, it goes from negative t to positive t, whereas this one starts at the origin and then goes the distance delta x until where the helicopter lands.
This is our group's real-world diagram for the situation. The helicopter starts at the origin of the coordinate system with x and y axes. The motion of the helicopter is highlighted by the curve here, which has the same curve as the motion diagram. Additionally, the helicopter starts at initial time at negative t and ends at a positive time t. This relates back to how much time the helicopter spends in the air, which was determined to be 2 times big T. Negative t to t is the same length as 2t, which confirms that statement. Additionally, you can see that the helicopter lands at a higher height than the starting height, demonstrating that the helicopter could have landed at a cliff. Finally, the total distance traveled by the helicopter was described by little d and was in the x direction and is shown at the bottom of the real-world diagram.
Now, continuing on with the sense making for the final answer, we need to find the unknown horizontal and vertical distance. Now, to do this, we're going to continue using the position equation, which we derive from the velocity, and the velocity, which we derive from the acceleration. So in order to do this, we need to, first of all, separate the x and y components. Now we do this by just taking the x component of the position equation and the y component of the position equation and set delta x equal to the x equation and delta y equal to the y equation. Then we need to simplify it a bit, which is shown on the right there, until eventually it comes out to one fraction with our two constants and our one variable time. Now, as we learned as I mentioned in the previous slide, little t is equal to big T. So substituting that in, we can now solve the equation for delta x, which is going to be equal to our total distance. And now that we know our distance, and we have it in terms of distance and time, along with our two constants, we can now solve that equation for time, big T. Then after finding big T, we can now use the equation for big T to substitute in for the variable big T in the delta y equation to finally find our vertical distance traveled, which turns out to be alpha over 35 beta times the distance, the horizontal distance. Now, the x and y components are eventually going to end up in the same spot, horizontally and vertically, because as mentioned previously, especially in the motion graph, the helicopter takes off, it goes up, then it drops down, and eventually ends up on what we set as the horizontal axis at x equals 0 there. At y equals 0, And yes, and then finally, the motion the helicopter undergoes, this is very similar to the majority of the flight patterns that aircraft would take, as in they take off at one point, they climb, till eventually they reach their cruising altitude wherever they want their max height for that flight. And then they descend and land, and that logically makes sense here if the pattern the helicopter takes, as it takes off at one spot, climbs, descends, and then lands again.
For sense making with units, I used the integrated position function that was shown in the project video. It was stated that the variables and constants in front of the x hat represents the change in x, while the variables and constants in front of y hat represents the change in y. These two deltas were simplified later in the video to d and 2 alpha t squared divided by 105. T is equal to square root 3 times d divided by 2 beta. The expected units for position would be meters. The units for d, or distance, are meters, and the units for t are square root meters. Since t is squared, the meters would also be squared, making the units of the function meters equals meters plus meters, which just equals meters. This matches with the expected units of meters for the position function. This situation is similar to the Super Mario problem that was completed in class. The problems are similar because we are asked to find the amount of time that Mario has a superstar and how long the helicopter is in the air for. Additionally, both problems have an unknown constant in relation to time t. Both problems involve the integration of acceleration function, a velocity function, to find the position function. The differences between the Super Mario problem and this problem is that the helicopter problem has two components, the x direction and the y direction. This adds a layer of complexity to the problem because we have to find how long the helicopter is in the air and where the helicopter lands, which involves finding the t constant, little t final, and little t initial, all to be found to find those objectives. Thank you for watching.